So humanity has its eyes on Mars. I mean, really has its eyes on Mars. Not just for a quick visit, but to actually stay. But building our first home on another planet, that comes with a massive challenge. How in the world do you construct a shelter when the planet itself seems like it's trying to tear it down? Let's get into it.
And that's the big question, isn't it? We've already proven we can land rovers and send orbiters, but going from just exploring to actually living there, that is a gigantic leap. To even begin to answer that, we first have to really understand what we're up against.
You know, calling Mars a fixer-upper might be the understatement of the century. Before we can even think about building, we have to wrap our heads around just how hostile the Martian environment really is.
I mean, just look at this comparison. Mars is so alien compared to home. The gravity is only about a third of what we have on Earth. Now, that might sound fun for a bit, but it messes with everything, from how you build things to human biology itself. And the atmosphere? It's barely there, and it's almost entirely carbon dioxide, totally unbreathable.
And then you have the temperature, an average of minus 63 degrees Celsius. Just to put that in perspective, the average on Earth is a comfortable 14 degrees. That kind of brutal cold doesn't just make things chilly, it makes traditional building materials totally brittle and basically useless. So what this all means is that any habitat we build can't just be a house. It has to be a fortress. It's got to withstand constant radiation, a toxic atmosphere, planet-wide dust storms, and these wild temperature swings that could literally crack steel. The scale of the challenge is just immense.
Okay, so how do you solve a construction problem that seems impossible? Well, you don't ship a whole construction site to Mars. You bring the factory. And this is where large-scale 3D printing completely changes the game. It's all about an idea called in-situ resource utilization, or ISRU, which is really just a fancy way of saying living off the land.
So, the first big decision is where to build. Do we go up or down? We could actually use existing underground caves or lava tubes, which would give us fantastic natural protection from all that radiation. But as you can imagine, trying to 3D print inside a cave is incredibly tricky. Building above ground gives you total design freedom, but then you're on your own. You have to create all that shielding yourself. It's a classic engineering trade-off. And why would you ship tons of heavy building materials 140 million miles when Mars is covered in them? We can literally make concrete from the stuff that's already there. One recipe involves mixing Martian soil, that's the regolith, with sulfur. It melts at a pretty low temperature, and it's great for blocking radiation. Or we could mine the basalt rock that's everywhere, melt it down, and create this incredibly strong, high-performance concrete. You know, on Earth, our buildings are all about fighting gravity, right? That's why we use columns and right angles. But on Mars, the real enemies are the internal air pressure pushing out and those crazy winds pushing in. So a dome-like, rounded structure is way more efficient. It handles those forces perfectly, spreading the stress evenly and letting those 67-mile-per-hour dust storms just flow right around it. Now, I know this might all sound like something out of a sci-fi movie, but believe it or not, it's already happening. To figure out how we're going to live on Mars, NASA is actually practicing right here on Earth, in a very, very special house in Texas. Say hello to Mars Dune Alpha. This right here is a fully 3D printed habitat where crews live for over a year at a time to simulate a real Mars mission. A company called Icon printed it, using a special concrete to mimic what Martian construction would be like. So this isn't just a concept anymore. It's a real, functioning research lab for deep spaceflight. And just check out this timeline. From the first designs in late 2020 to the very first crew moving in mid-2023, that pace is just incredible. It really shows you how quickly this technology is going from a cool idea to a practical, essential tool for space exploration. Think about it. Living in a small space for over a year requires some seriously efficient design. Every single area has to be meticulously planned out, from the private crew quarters and labs to the shared spaces for relaxing, exercising, and even growing fresh food. This is basically the blueprint for a real, functional off-world home. Okay, so the habitats we can build today are amazing, but the technology is moving even faster. The next generation of Martian construction won't just be about better materials. It's going to be about smarter robots and way, way smarter designs. So, what kind of robot do you send to Mars? A big frame or gantry system is super precise, but it's massive and can only print inside its own footprint. A mobile robotic arm, though, that is the clear winner. It can move all around the construction site, print much more complex shapes, and it isn't limited in size. It's really the difference between a little desktop printer and a truly autonomous construction worker. Now, to make these habitats both incredibly strong and incredibly light, engineers are using a technique called topology optimization. What that means is you basically tell a computer all the forces a structure will face, and the software algorithmically carves away every single piece of material that isn't absolutely essential for support. And what you get are these beautiful, organic, almost bone-like structures that are unbelievably strong for their weight. It is the ultimate way to get maximum performance from the absolute minimum amount of material, which is exactly what you need when you're building on Mars. We've been talking about building static structures, things that just sit there. But the future of this technology, it is anything but static. We're moving way beyond just 3 dimensions. So first up is 4D printing. This adds the dimension of time. Just imagine printing a flat structure that, when you expose it to a stimulus like the Martian sunlight, automatically folds itself into its final complex shape. That completely eliminates the need for complicated robots to assemble it on site. And then it gets even cooler. You've got 5D printing, which adds self-assembly. In this scenario, you could print thousands of individual components that then intelligently and automatically connect with each other to build a much larger structure. Basically, the printer creates the bricks, and then the bricks build the house themselves. And that brings us to the real frontier, 6D printing, which introduces adaptability. This is where a habitat is no longer just a static object. It can actively learn from and respond to its environment. Imagine a wall that automatically thickens itself to shield against a sudden solar storm, or an internal layout that reconfigures itself based on what the crew needs during a long mission. You know, we started this whole thing by asking how to build a simple shelter on another planet. But this journey has taken us somewhere completely different, to a future where our habitats are dynamic, responsive, and, well, almost alive. This technology isn't just about building on Mars. It's about completely redefining what a building can even be, anywhere in the universe.